Good evening, everyone. My name is Aditya Sharma, and this is a Power Plant System Engineering course being conducted by IIT Guwahati under the NPTEL program. And we are into the third week of our course. Okay, so the theme for this week still is Vapor Power System 1 as was in the last week. So there are two lectures in this week's content, and instructor for this course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati. I also am from IIT Guwahati, a research scholar, a PMRF. So we shall start in another couple of minutes. So let's wait for a few minutes and then we'll continue with the session. Okay, so I believe I can start with the today's session. So as I have already mentioned that the theme of this week's content is vapor power system again, vapor power system 1. So in the previous lectures uh, on this theme, that is lecture 3 and 4, we saw we were introduced to a Rankine cycle, right? And we compared it with our ideal cycle, Carnot cycle. Now, in this week's content, we want to increase the efficiency of our Rankine cycle, ideal Rankine cycle. And there are ways in which we can do that. So we shall see that in lecture 5. Then after that, in lecture 6, there is exergy analysis of vapor power systems. So exergy, as we have discussed in week one's content, that it is maximum theoretical work, right? So this concept we shall use here to analyze our vapor power system and see that how efficient a particular process is. For example, when we are trying to impart energy to our working fluid uh, in boiler. So energy from hot gases is imparted to your working fluid. So in that case, how efficient that process is. So to quantify that, we can take help of exergetic efficiency. So same way, different components, and we can find the different efficiencies. Okay. So let's see the topics of lecture number 5. So we shall proceed this way only, like we did in the previous tutorial. First, we shall see topics of one lecture and then questions based on that. Then topics of second lecture, then questions based on that. Okay. So your first lecture in this week's content. Just give me a second. Yes. So this is your first is your modified Rankine cycle. So we will modify our Rankine cycle in few ways. So that have been discussed. So first topic here is performance improvements in Rankine cycle. So as I was just telling earlier that we want to enhance the performance of our Rankine cycle. So how do we do that? So there are ways like superheating, right? Superheating your saturated steam, and then reheating is one more method. And third is your regeneration, where we use the energy from steam only, right, to heat our feed water. Okay, so that is regeneration. And then regeneration is of two types. One is your open feed water regeneration with open feed water heater, and then regeneration with closed feed water heater. So first we will see your superheat cycle. So what does a superheater does to a ideal Rankine cycle? So we shall see that. Then is your reheat cycle, then is your supercritical reheat cycle, then are your regenerative cycles, two regenerative cycles. So first let's see your superheat cycle. If you see in terms of TS diagram, so this is your ideal Rankine cycle, as we have talked about it in previous week. So this is, let's say this, okay. So this is your boiler. This is your pump, right? So now what we do is we superheat this, right? So now your vapor will be in superheated state, and this will expand this way, okay, from 1 dash to 2 dash. And this is your superheater. This is where your superheater comes into picture. So two things it does. This is your condenser. One is that average temperature of heat addition. Heat addition. It increases this. So what is the effect of that? So increasing the temperature of heat addition increases the your thermal efficiency of the cycle, right? In addition to that, it increases the quality of steam at your turbine exhaust, okay. And what is the benefit of this? So we want our steam exiting the turbine to be of quality as high as possible, so that this steam coming out of turbine doesn't corrode your turbine blades, okay. So that is the reason. So this is your superheat cycle. Then is your reheat cycle. So as the name suggests, reheat. So something is being reheated. And what is being reheated? Let's see that. So this is your TS diagram. So we have this, okay. So I'll draw it like this. Right. So what happens here is, so if you see, yes, so I can write this as this. From the above diagram, if I compare it, so 1 dash, 2 dash, 3, 4, and 1 is your superheat cycle. But then in the midway, when the steam is expanding from the turbine, so what we do? So I'll write this as 1 double dash, and this as 2 double dash, and probably this has maybe A. Okay. So what we are doing is, when this steam is expanding from 1 dash towards 2 dash, so in the midway at point A, when the steam is at point A, we reheat it. Okay. And then again it expands from 1 double dash to 2 double dash, and then it condenses to towards 3, and then here we have pump. Okay. So what this signifies is, so here if you see the quality steam quality increases. Okay. So this is your reheat cycle. Just give me 2 minutes. I will be right back. Okay, so I have just discussed the reheat cycle. Now, if you see your next performance enhancer, that is your supercritical reheat cycle. So if you see, so this is your supercritical reheat cycle. So let's draw the diagram first. This is your T, this is your S. So it is like this. Okay. So now what happens here? Your working fluid is heated above your critical pressure. Okay. And this leads to your increase in the efficiency, thermal efficiency of your cycle. And then second point is your this reheat. So this reheat takes place from your 2 to 3 when your steam is in the midway of expansion from 1 towards 2. So same as the previous reheat cycle, but just here the first time we heat our working fluid in the boiler, so that is done at pressure above the critical pressure of the working fluid. Okay. And for water, I believe that is 22.1 megapascal. Okay. But then if we have to heat this fluid at such high pressure and temperature, in that case, your this capital cost, okay, to set up the plant, this increases, this shoots up, right? But then because your efficiency has increased, in that case, that is a gain to you, but the capital cost increases in that case, right? All right, so this is your supercritical reheat cycle. Then next is your regenerative cycle, which is your open feed water heater. So what happens in your so let me draw that diagram first. So these two topics are now left in this lecture. Okay. So this is something like this. Hello, Satish. I'm just discussing lecture 5's topics. So after that, we shall see questions based on lecture 5. So I'm drawing the TS diagram for the regenerative cycle with open feed water heater. So what happens here is, if you see your this cycle, I'll just write down. If you see your okay, maybe I should not put it this way. So in this regenerative cycle, what we do is, when the steam is expanding through your turbine and it is in the midway between your condenser pressure and your boiler pressure, that is between point 1 and 3, somewhere in between. So we take some proportion of your steam, right? So let's say if steam is 1, then we will take some part, maybe 0.2, 0.3, or 0.1. Okay, just for example, I'm telling you. So we shall take some part of this steam, okay, and we mix this with, so let's say at in this direction, let's say y is going and what is moving forward is 1 minus 5, right? So this steam, okay, that we have taken from point 2, this mixes with our condensed liquid. Okay, this is condenser. So condensed liquid, that is coming from 4 to 5. Okay, and then here this will mix with this condensed liquid that has been pressurized by pump. Okay, right, and then your working fluid is heated using this heat that is present in your steam that was expanding and was at point 2. Okay, so this way we add heat to our uh, feed water, right? And what is the advantage of it? So eventually, if you see, now the boiler, the heat addition that is required at the boiler is from 7 to 1. Okay, heat addition is from 7 to 1. Okay, if the regenerative cycle had not been used, it would have been A to 1. Okay, in that case, more energy would have been required, right? So this is the advantage of your regenerative cycle with open feed water heater, right? Where your energy supplied reduces, but then also because we are taking some part of your steam while expanding, right, from the turbine, and this eventually leads to reduce in your work output. Okay, but then reduction in your work output is less than what you have gained in terms of your reduction in your energy supplied, right? So this is your regenerative cycle. Okay, after that is your last topic of this. So you have last topic of this lecture number 5. So let me draw the diagram first. So in the previous cycle, it was open feed water heater where your working fluid coming from your pump was being mixed with your steam that you have taken from point 2, right? But here in closed feed water heater, your line that you have taken from 2 doesn't directly mix with your feed water. Okay, so it just exchanges heat at point 5. So this steam that you are getting from your point 2 So it exchanges heat at your point 0.5 and your working fluid reaches your point 0.6. So it helps in your working fluid to reach from 5 to point 0.5 to 0.56, right? And after this has been done, your this steam that you have taken from 2 is your captured by your condenser, okay? And then it reaches at your point number 8 from your point number 7. And then these two streams come together, and through pump is again pressurized towards point number 5, okay? So let's say if this is y, this is 1 minus y, so this also will be 1 minus y, so this is y, okay? Eventually here y and 1 minus y means the whole working fluid that started from point 1. So your pump will receive the whole fluid, okay? And this way will move towards the boiler. So same is the case with your closed feed water heater regenerative cycle also. Here also you reduce the energy that is supplied to the cycle, but at also the cost of your reduction in the work output from the turbine, right? But then the loss in work output is less, okay? And then the uh, energy supplied, right? So the when we compare the energy supplied and working fluid, this work output from the turbine, we in summation we are at gain. So this is the whole idea. All right. So this is your closed feed water heater. Okay. So these are the topics related to your lecture number 5. Okay. So now let's see the questions based on your lecture number 5. So this is your first question. So you can read this question first and then try to answer. So the question says that read the statements given below and choose the correct option. So two statements are there, and then based on these two statements, four options have been given. So you have to choose the correct option. So your statement one is, so in the context of vapor power cycles only, so this has been, statements have been given. So a common practice is to maintain steam quality at least 90%. So this is your first statement. And then statement two is the low quality steam corrodes the turbine blades. So which of the following options is correct? So your statement, sorry, option one is statement one and two are correct, and one is the correct explanation of second. B option is both are correct, but one is not the correct explanation of. Sorry, it should have been two is the, and here one. It should have been like this. Okay. So this is your 2 and this is your 1. This is your 1, this is your 2. Okay. And then statement 1 is incorrect and statement 2 is incorrect. So which of the options is correct? So if you see your statement 1, this is correct because we don't want our steam to be of poor quality. Otherwise, it will corrode the turbine blades, right? That again will increase the maintenance cost of the whole cycle. And then your statement 2 says that low quality steam corrodes the turbine blades. So this is also correct statement. And your if you see your option A, so this is the correct option. Both the statements are correct, and second statement is the correct explanation too. Your first statement. Okay. So this was your question number 1 based on lecture number 5. Now let's see the next question. Next question is, with regenerative feed water heating, the average temperature of heat rejection is decreased. That tends to increase the thermal efficiency. So whether this is a correct statement or not, you have to answer this. Regenerative feed water heating. So if you see your regenerative feed water heating right here. So these two cycles, if you see, so here the heat addition reduces, right? So your energy efficiency increases. Then your work output also reduces. But then your in no case your average temperature of heat rejection is being touched. Okay. So when the statement says that, because a statement proves to be tempting, so statement proves to be tempting because the second half of the statement says that is correct, right? So average temperature of heat rejection is decreased. So if average temperature of heat rejection decreases, that eventually leads to increase in your efficiency, right? But then in the context of your regenerative feed water heating, whether that is correct or not, so that you have to see. So in this regenerative feed water heating context, this is not correct. In that case, this comes out to be a false statement, right? So this is your second question. Then let's move on to the next question. Question number 3. So please read the question. Question says that with the introduction of a superheater in the ideal Rankine cycle, the average temperature of heat addition. So obviously, if you see, first you see your, because the question talks about superheater. So then we will go to superheater. This is superheat cycle where we have superheater. So let's say first we had this temperature only T1, but after superheating we have this temperature also, okay, in picture. So the average temperature of heat addition, sorry, whether it increases or decreases, so clearly it increases. And what is the effect of that? The efficiency increases, right? Increases. Your thermal efficiency increases, right? That is TH minus T cold by TH, right? This is your thermal efficiency. That increases. So this was your question number 3. Pretty basic questions. Then is your question number 4. So few statements are there. And you have to tell that out of these statements, which of the statements are correct and which are not. So you have to just tell which of the statements is or are not true. So 4 options are there. So you may read the 4 options and try to answer. True. So this is about supercritical. Sorry. Power plants. So now this is complete question. So this is about supercritical power plants only. Three statements are there. First statement says that your supercritical power plant operates with steam generator pressures greater than the critical pressure of water. So if you see your the super critical reheat cycle, you can see that your pressure at which your working fluid is being heated is greater than your critical pressure, right? So this is somewhere here is your point of criticality for your working fluid, but then this is above this pressure. Then the fuel cost is considerably low in comparison to ideal Rankine cycle. So that is correct. This is correct. So this is also correct because it says that it is greater than. Then thermal efficiency is high in comparison to the ideal Rankine cycle. So this is also correct. So none of the given statements is false or incorrect. In that case, the correct answer to this question is option number D. I hope that is clear. So this was your question number 4. Option D is correct. Now moving on to your next question. That is question number 5. So it asks from us which of the following statements is true about regenerative cycle with open feed water heater. So which of the following statements is correct? Or you can say options. About regenerative cycle with open feed water heater. First is your the energy supplied from combustion of fossil fuel increases. So the energy supplied through the fossil fuels in the boiler to your working fluid, this increases. So if your energy supplied will increase, it means your cycle is becoming less efficient, right? Then it says that there is increase in work output. If work output is increasing, also the input energy is increasing. So at least some gain is there. But whether this is correct for your open feed water regenerative cycle with open feed water heater or not, so that we have to see. So we have seen in the regenerative cycle with open feed water heater that your energy supplied decreases, because if you see your open feed water heater, so without this regenerative cycle, the boiler would have taken path from A to 1, but because of open feed water heater, this is shrinking to the path from 7 to 1. So which essentially means your heat amount of energy addition has reduced. Okay. So first statement is not correct. So question asks which is correct. So there is increase in work output. That is also not true, because if you see, you're taking some amount of your steam from point 2, right? So which means the expansion is not of the full working fluid that has entered the boiler, that had entered the boiler. And in comparison to a normal cycle, normal expansion, this will result in less work output, correct? And which means your B option is also not correct. Then it boils down to that your C is also not correct. So none of the above options is correct, right? So D is the correct option to this question. Okay. Now after this, we have numerical questions. Okay. So we have four numerical questions based on Rankine cycle. So I'll just share a link with you guys for the steam table. So you can use that link to access steam table, or if you have a steam table of your own, that is also fine. So I have shared the steam table link in the chat, so you can see that. Okay, so let's take a short break because it's almost 1 hour since we have started this session. So we can continue after a short break. Okay, so we can continue with the session. So information has been given for question numbers 6 to 9. Okay, so the information says that we have a Rankine cycle, and then we have saturated vapor that enters the turbine at 85 bars, and saturated liquid that leaves the condenser at 0.15 bar. The net power output is 95 megawatts. Then we have to solve the questions. Okay, so determine the thermal efficiency. So first is your this question number 6 to 9. What has been given? Let's write that first. Pressure at which this heat is added, right? This is your 85 bars. And then condenser pressure is your 0.15 bars, right? Then after that, your W net is given as 95 megawatts, I believe. Yes, 95 megawatts. Now we want to calculate the efficiencies. But if you see, efficiencies require enthalpies, enthalpy data. So this is your Rankine cycle, correct? So I'm drawing an ideal Rankine cycle. This is like this. Okay. This is your pump. So these things are here. So this is your ideal Rankine cycle. Now this pressure has been given at 85 bar, and this has been given at 0.15 bar, right? So for your efficiency, if you see, efficiency is turbine work minus pump work W by Q in, right? So this is your efficiency. But then to calculate these, you need enthalpies at 1, 2, 3, 4, right? Correct? And for Q in also, you need enthalpies at 1 and 4. So we need to know these enthalpies, right? Now, how can we do that? So, because we know that when the working fluid enters, it is in saturated state, right? So this is saturated state. And here this is saturated vapor, right? This state. See your this state, and if you see your this state, this is, sorry, saturated liquid. This is your saturated liquid. So from the steam table, we can have the properties. So I have given you the link. So you can open that link. So if you see here, this is the link. Now if I open this, so this is your table for saturation temperature with respect to saturation temperature, right? Now if you see your table number 2, this is related to saturation pressure. And here if you see, so this is if you see the leftmost column, so this is on pressure. So their pressures have been given. So 0.15 bar, if you see, 0.15 bar has been given. I won't be able to mark it here, but then yes. So 0.15 bar, and then your 85 bars, also 85 bars has also been given here. So this is your 85 bars pressure. So corresponding to these two pressures, we can have the, if you see the first row, the topmost row, if you see, so the enthalpies have been given for your fluid state. L, it has been, fluid state has been represented by L. So we'll write it F for our purpose. Then for gas, it has been given. And then R is your H subscript Fg. That is your mixture, vapor liquid mixture, right? And the same way we have entropies for your liquid state, and then gaseous state, and then for your mixture state, right? And then again we have the specific volume we have, right? So the column for specific volume. So from this data, we can get the values, right? So now coming on to our sheet. So let's write down the values. So at 85 bar, this is okay. Hg equals to h1. Why Hg is equals to h1? Because at point 1 your working fluid is in gaseous state, right? Okay. Then hfg is equal to, okay, this is your enthalpies, and then your entropy. This is your fluid and this is your gas. This is your, right? So this is also equal to your S1. Then SFG is equal to, all right. Now similarly at 0.15 bar, the values we will see. So this is, if I am doing somewhere mistake, you can write down in the comment box. the link for the Steam table from where I'm taking these values I have already given to you. Okay, so this is it. So enthalpies are done. Now entropies. Yes, so because at point 3, if you see, it's in saturated liquid state. State 3 is of saturated liquid states. That is why we are giving the third state to the subscript F. Okay, then Sg is and Sfg is equal to right. We will also require this somewhere, so I'll also note this down. So that's it. Now, so if you see your requirement for your question number 6, you want work for turbine, for pump, and then heat input. So for heat input, you will require H1 and H4, right? So from here you can see we have H1, we have H3, we don't have H4, right? And also we don't have H2. So we need to find these values, right? So how can we find that? So let's see that. So if you see, now you see H2, okay? H2 equals to H2 can be written this way, right? H2 can be written this way. Here we have H3, we have H2FG, but do we have X2? We don't have. So how can we find out X2? So what we will do is we will use the data related to entropies. Okay. So from the data related to entropies, you see from 1 to 2, if you move, that is isentropic, right? So if you move from 1 to 2, 1 to 2, if you move, that is isentropic. So which means entropy at 1 and entropy at 2 will be same, right? And entropy at 2 can be written as S3 plus X2 S2FG. It can be written this way, right? Then S1 we know what is. This is this from here you see, right? This is your S1, right? And S3 also you know, which is 0.7548, right? And then but X2 we don't know. So there is only one unknown here that we can work out, right? So if we work this out, this will come out to be, so if I have made any calculation mistake, you can just comment it down. Okay. All right. So this is 0.6832. So x2 is this. So x2 comes out to be this. Now we can find out our h2. So h2 becomes h3 is 225.95, x2 is this, h2fg is, and calculating this gives this. Okay. All right. So now we have h2 also. H1 we had, H3 we had, we calculated H2, but now we want to calculate H4 also because that is also required to find heat added. So how can we find out H2? To find, sorry, H4, how can we find out H4? So to find out H4, yes, what we can do? So we can use this expression. H4 equals to H3. All right. So we have learned this in our lecture 3 and 4. So this expression somewhere in lecture 3 and 4 we have learned this. So we can use this. H3 we know, correct? And this is your V3 basically, or new 3. So 0.001, 0.01405. So this is in meter cube per kg, right? And this is in your megapascals, but then we want it in kilo. So this is in bars. Bars is 10 raised to power 5, but we want it in kilo, so we will multiply it with 100. And then this comes out to be 234.5542 kilojoule per kg. Please check this out, whether this is correct and whether the 100 I have introduced is correct or not. Okay. So now even H4 we have. So now we are prepared for our question number 6. Okay. So let's now solve the question number 6. So NT is W net by Q in. W net is W turbine minus W pump. W turbine is H1 minus H2 equals to 2750.1 minus 0.7053, right? So this comes out to be 903.3947 kilojoule per kg, right? And then this pump work, if we see, this is H4 minus H3, which is 8.6042 kilojoule per kg, right? And then Q in is H1 minus H4. And if we solve this, this comes out to be 2515.5458 kilojoule per kg. Okay. And now calculating the thermal efficiency. So this will be turbine work minus pump work divided by Q in. So this is 903.3947 minus 8.6042 divided by 2515.5458. And if we solve this, this will come out to be 0.3557. That basically is 35.57%. So this is the thermal efficiency for this Rankine cycle. So this was your question number 6. Now let's see question number 7. So determine the mass flow rate. So how do we find the mass flow rate? So W net we have been given, right? So W net has been given as 95 megawatts, right? And W dot net we have calculated in this. So if you see the numerator of this, that is W dot net. So this will, if you work this out, this will come out to be 894.7905 kilojoule per kg. Okay. And W net equals to mass flow rate into W dot net implies mass flow rate equals to W net divided by W not net, so, net dot net. Sorry. So now work this out. Megawatts. So everything is in kilos. So we will multiply. We will convert this into kilowatts, and the numerator already is in kilo terms. Now, if you solve this, this will come out to be so this is your mass flow rate of your steam. Now moving on to question number 8, solution. So the same way, now you want to find out what? So this is your mass flow rate. Now you need to find out rate of heat transfer. Now you need to find rate of heat transfer. How can we find? So we will multiply the Q dot in with so this you will do. So if you do this, Q dot in we have already calculated, which is 2515.5458. But this is all in kilos, and the question asks in megawatts. So to do that, what we will do? We will divide this with 1000, right? And if you do this, this will come out to be this, right? So this is your question number 8. Now moving on to the last numerical of this lecture. Question number 9. Now it asks for heat transfer from the working fluid in the condenser. So that heat which is being rejected, how can we calculate that? So the same way, Q out is m dot. So heat rejected is from which state to which state? So this is from when we move from state 2 to state 3. So heat is being rejected. Okay. So 2 is at higher end and 3 is at lower end. So m dot we know. So all this is in kilo terms, but then we want it in megawatts terms. Okay. So if you work this out, megawatt. So this is your Q out. So this was your question number 9. Okay. I hope there is no doubt in this numerical. If there is any doubt left, you can just type in the comment box and I can answer there also. Okay, 172.07. All right then. So moving on to the last lecture, that is lecture number 6. So as I have already mentioned, this is the concept of exergy. So exergy basically is the maximum theoretical work that we have in our hand, right? So let's see the topics one by one, and then there are 3 questions based on this lecture. So first is your so this is exergy analysis of vapor power cycles. So if you see the topics, first topic is vapor cycle exergy analysis, where concept of exergy, exergetic efficiency, then heat exchanger unit without mixing, then turbines, pumps, and condensers. So this has been discussed from the perspective of exergy. Okay. Then in the second heading, some other vapor power cycles have been also discussed. So for example, organic cycle, right? Where we are using some organic working fluid in place of water. Okay, so that is your organic cycle. Then is your binary vapor cycle. So this is a bit interesting. So there are 2 separate cycles in your binary vapor cycle, right? So what happens is that one cycle is operating at higher boiler pressure and condenser pressure in comparison to the second cycle, and the one that is taking place at higher pressures and temperatures. So the condenser for that cycle, the heat that is rejected from the condenser of that cycle, which is operating at higher temperatures. So heat rejected from that cycle is being used to heat the working fluid in the second cycle, which is operating at lower temperatures. Okay, so that heat rejected from the higher temperatures cycle is being given to the boiler of the cycle with lower temperatures. So this coupling of 2 cycles has been called the binary vapor cycle. Then is your nuclear power plant, right? Steam cycle for nuclear power plant. So here fuel is your nuclear fission, right? So in nuclear power plants, nuclear fission takes place, and then this energy from here is carried by some secondary fluid, right? So primary is your water for the steam power cycle, but then this water has to be heated, and the energy is carried with some secondary fluid. Okay, the energy that has been dissipated from the nuclear fission in your nuclear power plants. So this secondary fluid carries this heat and exchanges with the working fluid. Okay, so this is your nuclear power plant. Then is your low temperature power plant. So low temperature, why the name low temperature? Because here even your boiler works at low temperatures. And why so? Because the mm, energy that we are receiving is from our sources like solar energy, right? Geothermal energy. So these are the sources of energy, right? Which have their capacity to raise the working fluid's temperature to a certain level only, right? So this is your low temperature power cycle. And then last is your cogeneration, where we couple our vapor power cycle with some other power cycle, for example, gas turbines, right? So we shall briefly and quickly see what are all these topics. Okay. Right. So this is your lecture 6. Okay. So here is your lecture 5. So first is your concept of exergy. So this we have discussed this in week 1, right? So I'll just this is maximum theoretical work. And how do we calculate? We calculate this maximum theoretical work by comparing it with dead state or environment, right? Right. And one point about exergy is that it cannot be negative. One more point is that it is not conserved. So this can be destructed. Okay. This is your exergy. Then is your exergetic efficiency. So what is now exergetic efficiency? So let's say we have given some heat to some system, right? And why we are studying exergetic efficiency? because in our vapor power cycle, this is of help to find the efficiency of the components. So it has been explained in lectures like this. So for example, sorry, we are giving heat like this, and heat is being used at temperature U, and this heat is reaching. So this you can compare with the boiler. So let's say this is being given to the yes. So this is being given to the boiler, and QS basically is the heat that is available when your fuel gets combusted. So this is the heat that is available. But then the heat that uh, reaches to your boiler is this much only, right? So here your some heat, some energy gets lost energy, right? So now when you want to calculate the exergetic efficiency, so exergetic efficiency is written as this. So you can put it this way, right? And then next topics are on heat exchangers and then turbine pumps. So I was telling that for the elements of vapor power cycle, vapor power plants, we can use this concept. So for heat exchangers, if you see, this exergetic efficiency can be written in this way. So E basically is, this is your specific exergy. Okay. And what is 1 and 4? So this has the same meaning. So maybe I can draw once again. So this is your Rankine cycle. So here now you see positions states 1 and 4. Okay. So they, so this is basically this. Okay, and 4 is, this. Okay. So these are the states, right? So in heat exchangers, if you see, as far as the heat exchangers are concerned, so numerator talks about your boiler. Okay. So difference in exergy when the working fluid enters and when it exits. Okay. So numerator talks about that, and denominator talks about your hot uh, gases that have combusted, right? Hot combustion gases. So subscript I is for initial. Initially, what was the exergy of the hot gases and when they exit the heat exchanger. At that time, what is the exergy, right? M dot subscript A is the mass flow rate of air, right? So this is for your exchangers, heat exchangers, right? So the similar way we can write this for condensers also, but just let me confirm one thing. Whether this what I have noted down is correct or not. Okay, I still have doubt on it, but that is fine. Okay, so the similar way we can write for condensers also, right? But because I have a doubt with condensers, so I won't just. So this for condensers, it can be written this way. So subscript CW is cooling water. So this. Okay. So this is for your condenser. So I have doubt on the sign here, but that's okay. So this has been given in your lectures. Okay. Then is your other vapor power cycles. So I have told you what is organic cycle is, where you are using some organic working fluid, right? Which has boiling point lower than water. Okay. So that becomes easy to attain the gaseous state. Then binary vapor cycle I'll draw. So as I was earlier mentioning that two different cycles. Okay. So first is this cycle. Okay. Then this is condenser. This is, let's write 1, 2, 3, 4. So this is your condenser of cycle 1. So I'm calling it cycle 1. And what we do, So we take heat from here. So write this as 1 dash, 2 dash, 3 dash, 4 dash, and then join this. So this is boiler of cycle 2. So condenser of cycle 1 is acting as the heat from rejected from condenser of cycle 1 is being used for the boiler of cycle 2. Okay, so this is your binary vapor cycle. I hope there is no doubt in binary vapor cycle. Then is your steam cycle for nuclear power plant. So I have discussed this briefly. Low temperature power plant power cycle also I have discussed. So cogeneration. Let's say this is your gas turbine and this is your vapor power cycle. So what we do, the exhaust from this gas turbine cycle, right? These will be hot gases. So these we are giving to our vapor power cycle, right? Heat exchanger. So the energy that is with the hot combustion products from the exit of gas turbine. So this is one example. That is the energy from that is being heat from that is being used to boil the water of some vapor power cycle. And this coupling of two different power systems is known as cogeneration. Okay, so this is your cogeneration. Then let's see the questions based on. Okay, for a dash, the flow exergy increases from inlet to exit. So clearly, we lose the exergy in turbines, right? The working fluid expands, the steam expands, and we get work output, right? And the steam loses its exergy, right? The working ability. But in case of pump, the case is opposite because we pressurize the working fluid, we work on the working fluid and it increases its exergy, right? So option A will be correct for this question. All right. So this was question number 10. Moving on to next question, which says that in a binary vapor cycle, the condenser of topping cycle acts as boiler for bottoming cycle. So question asks about binary vapor cycle and the condenser of topping cycle and the boiler of bottoming cycle. So the cycle with higher temperatures is the topping cycle. So this is your topping cycle. Okay. So cycle 1 is here, this is topping cycle, and this is bottoming cycle. Okay. So questions, sorry, when the question asks that the topping cycle, condenser of topping cycle. So this is condenser of topping cycle. It acts as boiler for bottoming cycle. So this is your bottoming cycle and boiler for bottoming cycle. So heat rejected, which essentially means that heat rejected from the condenser of topping cycle is being used as heat that is being added in the boiler to the working fluid. So whether this is correct or not, so this is a correct statement, okay? Because that is what is happening in vapor power cycle. So last question is on cogeneration. In cogeneration, a steam cycle is integrated with other power cycle. So whether this is correct or not, so pretty straightforward. So this is what cogeneration is, right? So some basic questions so that you are able to revise these topics. And also we saw numericals in question number 6 to 9. Right? So this was it about today's session. And I'll conclude this. So this was again theme vapor power cycle 1, where previously we were introduced to Carnot cycle and Rankine cycle, then ideal Rankine cycle, right? And here we started with the intention of improving the performance of the ideal Rankine cycle, and that we did through your reheat cycle, regeneration cycle, right? And through supercritical power plants or through superheat cycle, we did that. And after that, came to the we came to understanding the efficiencies of different parts of a power cycle, vapor power system. Okay. And in that effort, we brought the concept of exergetic efficiency, where we saw the exergetic efficiencies of condensers and then your boiler heat exchanger. So how we can calculate all that, right? Okay. And we discussed some very basic questions based on these two lectures, and also we did four numericals based on Rankine cycle. So this was it about today's session, and thank you for watching the session, and we will again meet next Tuesday at same timing from 6 to 8 p.m. with next week's content. Till then, thank you for watching this session, and bye.